关系不是那么紧张吗？回头慢慢再等等，或者打个电话问问。
So the next thing we're going to look at is regression estimations. And well, this is probably the simplest thing you can do in terms of statistics. So quadratic programs, are comparably difficult when you compare them to simple regression estimators, least mean squares problems that you could use. So, and we are going to use exactly the same strategy as what we had before. Remember, before we had the risk minimization. You get the function, you take the empirical average, you get a convex upper bound, you add a regression term, and you minimize. And we do the very same thing here. We take some function f, minimizing the regression error. That's what we would like to have. But of course, we don't really have the entire distribution. We only have an empirical average from that. In which case, well, we could actually get significant overfitting if we just want to minimize the empirical error here. So the idea is you add some regression term that will ensure that capacity control is maintained. So in other words, I want to make sure that I don't just fit all the data entirely, but I want to at the same time also have a function that's reasonably well behaved, reasonably similar. So for instance, if you think about polynomials, I might penalize a lot if I have higher order polynomial coefficients in my regression estimators with very large weights. And I might have to specify a trade-off, how much worse is it if I have a fifth order coefficient rather than maybe a second order coefficient. And those kernels that I showed you before, those polynomial kernels, will do exactly that for you. And we'll look a little bit more at function spaces and so on next week, but that'll be fairly heavy on Fourier transforms, special function theory and so on, if you want me to go into that detail. So let's put things a little bit more into context. So I could have a squared loss. Everybody's seen that before. I could just minimize the deviation between observation and estimate. I could have even an epsilon sensitive loss, and that was the one that was actually put forward when SVM regression was published. And so for a while people thought, okay, if you have to do support vector regression, you have to use this loss, right? This loss is kind of nice, but it's not so amazingly nice. I mean, people were probably more obsessed about that than I was. I mean, this was, I think, my first paper I ever wrote. But a lot of people still think that support vector machine regression has to go with that loss. Let's just do something very simple here. Take a least mean squares problem, right? So we have yi minus xi dot w squared, and actually it should be 1/2 up here, plus lambda over 2 normal w squared. So taking the derivative is going to give me, well, what do we get? We get, the 1/2 goes away with the 2 up here, so we get xi times xi transpose w, that's what I get from this term here, minus xi times yi. Sum over all the I from 1 to m. And I add to that lambda times w. Now, that looks intimidating, and I can make it a lot simpler if I write it in matrix notation. The matrix notation, this is simply 1 over m xx transpose plus lambda times the identity times w minus 1 over m x times y equals 0. And so, I get in the product here plus lambda times m times identity inverse times x times y. So, this is a matrix inverse. I can be fairly unpleasant. Right? As a matter of fact, at the moment, this object here is still as high dimensional as my data. So if this is if X is in a million dimensional space, and I have 100 instances, that's, you know, a million by a million matrix with rank 1 million, with the add identity element there. Likewise here is a million dimensional object. So that's not very practical yet. What you want to do is, you want to write that actually in terms of kernels to get an efficient problem that you can solve. So what we're going to encounter in this context is the representer theorem. At least the first instance of it. We'll prove it formally next week. But basically, what you've already seen in one or two cases is where I say, okay, things work out quite nicely. We can expand things in terms of, you know, our data points, and so then everything, you know, is projected down to this lower dimensional space, which is just, you know, as high dimensional as how many data points we have, rather than the original space we worked with. Now, this always looks like a lucky coincidence, but that's actually a theorem underlying it. It's called the representer theorem. Probably one of the earliest versions of its proof is by Griswold. Actually, let's just prove it right away. Maybe if you could move the camera over. Thanks. So there are lots of different proofs for it. So it basically, the formula I'm going to prove goes as follows. Suppose I have the following optimization problem I want to minimize with respect to W, the form, an expansion of the form I equals 1 to m, some loss function which depends, amongst other things, on W not xi. I'm not really specifying what those xi's need to look like. And then I have, in addition to that, some other function omega, which depends on the norm of W. And just to make my life a little bit easier, I'll just make it the norm squared. Just because it gets easier, but you can always make that happen. Then the solution of this problem has to satisfy the property that W is sum over alpha I xi. Okay. Now, that's actually very easy to show. What I'm going to do is I'm going to decompose the space in which the W's live into a space that's given by the span of those xi's and an orthogonal component to that. So if W is in some Hilbert space H, I'm going to write this as H plus H parallel direct sum plus H orthogonal. Okay? So I can always do that with the Hilbert space. Now, what I can therefore do is I can decompose W as W parallel plus W orthogonal. And I know that for any W that's in H parallel, I can write it as this expansion. So therefore, all I have to show is that any orthogonal component to that span has to vanish. Right? Now, the first term here, if we just decompose it into W orthogonal plus W parallel, I know that the orthogonal component cannot actually change the function value. Right? Because it's taking an approach with the xi's and that lives in the span. Now, for this regularization penalty, what we get is that this is W parallel plus W orthogonal squared. Right? So it's just Pythagoras. Just you know, these are orthogonal components. Now, therefore, the optimization of a W orthogonal is just in terms of the second argument. And if I assume that omega is monotonically increasing, I don't even require convexity, but just monotonically increasing in its argument, that already implies that the best thing I can do is I can make this term go away. And that proves the theorem. Okay. So, okay, so which part would you like?
Last part.
Okay. So I decompose W into W parallel plus W orthogonal. By the way, can you actually read the stuff from back?
Yeah.
Wow, your eyes are good.
I like that.
Okay. So I don't think I could. Congratulations. So that orthogonal part here just adds to the squared norm. Now, if I want to minimize this expression here, if I want, you know, for given W parallel, the minimizer in W orthogonal has to be the one where W orthogonal is 0. And that's it. So therefore, W has to lie in the span of these xi's and the theorem is proved. Okay. This is an extremely simple proof, right?
So do you only talk about the autonomic?
What?
So you only talk about the autonomic?
So this has to be in a Hilbert space. So L2 would be a Hilbert space. But there are lots of other Hilbert spaces. As a matter of fact, what we'll see is that the kernel will induce a Hilbert space, and these Hilbert spaces will be called reproducing kernel Hilbert spaces. We'll do a lot more of this theory next week, but I first want to get you up to date on, you know, the basic tools of SVMs. We'll do more optimization, structured estimation, and so on. All of that next week. Yep.
So you do assume that omega is monotonically increasing in
Yes.
its argument?
Yes.
Is there also a reason why the loss function has an index I?
Yes, because it might depend on yi.
Oh yeah, that's
So I'm just hiding all this. So I'm just, as a matter of fact, I wouldn't even need that. All that I would need is just that I have some function L, right? Some function L, which depends on w dot x1 up to w dot x. That's really all I need for that. Okay. So there's a funny story about this theorem. So I mean, the proof is really simple, right? I mean, I managed to explain it in like 2-3 minutes. It's actually a fairly fundamental theorem in terms of, you know, what you can and cannot do in terms of, you know, kernel methods. Now, when we wanted to publish this at a conference called Computational Learning Theory, we submitted it, and the referees liked it, but then they said reject because the proof is too simple. Okay. The following year, we resubmitted it. And we added something to it which made the math look impressive and didn't actually change the main statement. And it was happily accepted. Nobody cites the paper for the impressive math. No, I have not seen a single instance of that. But I've seen a lot of people referring to the paper for the simple theorem and the simple proof. Okay. So, use that advice in whichever way when you write your next paper. Basically, put the simple things that you think will last somewhere. Make it easily accessible. And then, if you need to, add the more technical parts that might sway a referee who doesn't see the simple parts. But don't necessarily try to obfuscate things if you don't have to. Okay, so here's the epsilon sensitive loss that I showed you before. So, you know, when you might have something like that. If, for instance, if you have a manufacturing problem and you have certain tolerances, and you know, maybe you have a manufacturing contract and it says, well, you know, all of your, you know, shiny new iPhone screens must have, exactly 3.5 inches wide, and you allow, for 1/10 of an inch tolerance, and anything within that bin is good. Anything outside the bin, well, okay, the Apple doesn't buy it, right? So then you would have actually more this kind of loss, because anything that's outside here you have to throw away, or you basically pass it on to somebody else. So here's the optimization problem. So this looks a little bit messier, right? But there's nothing really intimidating to it. It's exactly the same reasoning as what I showed you before, but just that now we have 2 constraints for each observation, and we have a few more variables. I'm going to spare you all the details of the Lagrange function. As a matter of fact, you can read through that at home if you want. But here's what happens. So here's our penalty again. We basically, in this case, want to find the flattest function for whatever reason. Plus, here's the sum of the slacks. And now one of the conditions is that w of xi plus b, so that's my estimate, is less equal than yi plus epsilon. And if I really can't make it, then I have to pay this slack variable price psi I. And furthermore, that w of xi plus b is greater or equal than yi minus epsilon. And if I can't make it, here's the additional penalty psi xi. And then you crack the handle. And, crank it again. And you get this dual problem. Now that looks a little bit more complicated, right? But effectively it's the same flavorful problem. Now we have twice as many variables, alpha minus alpha star. Here we have alpha plus alpha star and so on. But the good news is that the number of non-zero terms doesn't really increase very much. Because, first of all, it actually ignores typical instances with small error. And obviously only either the lower or the upper bound at all may be active at any given time. Because I cannot be violating the upper and the lower constraints simultaneously. And the quadratic program, okay, now it's in twice as many variables, but I can still efficiently solve it. One nice thing is it's robust with respect to outliers. So if I wanted to have just an L1 problem, all I would have to do is I just set epsilon to 0, and I get exactly L1 with square penalty. So you just make this term disappear, and then you can actually have a variable transform where I will get basically beta transpose k beta plus y transpose beta under the constraint that 1 transpose beta equals 0, and beta is in the range between minus c and c. That would be the corresponding L1 problem. So it's very simple. Let me show you a few examples. Well, this is the Mexican hat, which I think out of boredom I implemented when I first worked on that, and then a lot of people replicated the Mexican hat because, so keep in mind what you use as, a test example on any problem where you write a paper about. People might redo the very same thing whether it makes sense or not. And okay, you can see that the larger the margin, the flatter, the smoother the function that you're getting. And here are some of the support vectors. You would see that if you impose a rather tight tolerance, you get a lot of them. If you impose a very loose tolerance, you're going to get, in this case, 3 of them. So you have a trade-off also in terms of compression. Now that's kind of cute, but actually this is the loss that you should be using. So, as a matter of fact, this is the fancy version of a trimmed mean estimator. So if you have any regression problem, seriously consider this loss rather than least mean squares. And the reason why it's better than least mean squares is that basically if you have very large deviations, at some point you don't pay anymore for a large deviation, so it becomes more robust to outliers. That's actually going to be near assignment. So think about why this will give you a trimmed mean estimator. Okay. Now, essentially, think of it this way. You have all the data points, and you have this loss function. You can essentially move it around. You can move this, parabola-like shape around, and think about how many points you need on the left and the right, and what happens in the middle. So it's basically quadratic up to here, to 1, and then linear as you go beyond that. There's a very beautiful theory of robust estimation that goes with this. Any questions at the moment? Everything fine? Everything clear? Okay. Let's move on to novelty detection. And we're covering a lot of ground today. So, what's the basic idea? Well, I have some observations XI that may, be generated from, some distribution. Like, for instance, network usage or handwritten digits, alarm sensors, how my factory is doing, how my server center is doing. And what I really want to be able to do is I want to find unusual events, or clean my database, or find out which instances are really typical, or if I have a customer-facing product on the web, I want to find out when maybe somebody's trying to run a denial of service attack or just do something else that's very strange. So fraud detection. I mean, there's a lot of stuff where you have, for instance, your credit card transactions, and you want to really flag the very unusual ones, or phone bills, or medical records. That's a big deal. Or a simple example, and it's actually unfortunate that nobody's built this thing yet, is self-calibrating car alarms. So, who's had his car alarm go off at night at some point? Okay, not so many people drive cars here. Okay, maybe South Bay. Okay, or somewhere in suburbia. Okay, so it's an extremely annoying thing if your car alarm goes off. And basically, when you install this darndest thing, you have a problem, right? Because if you make it not very sensitive, then okay, it won't go off at night and not going to wake up the neighbors, but then it might not even detect when the thief really smashes the window and bad stuff happens. So you can make it more sensitive. If you crank it up to a higher level of sensitivity, bad things also happen. The neighbor drives by with his truck or with his motorbike, the entire air vibrates, the sensor goes off, and the neighbor wakes up. Different neighbor. So, obviously, neither of those two is particularly desirable. So what you would like to be able to do is to have a system that automatically adapts and calibrates for the environment. And then, basically you have an op which says, one false alarm a week, or one false alarm a year, right? You set it. You set it according to how much you want to know your neighbors. So, how can we do this? So the first thing I could do is I could just do density estimation, right? And the idea is novel data is the one that we don't really see very frequently, so it must be in the low density region. So what's more natural than to just go ahead, estimate the density, which I could use Parsing Windows, right? Or I could use anything else for that. And then I threshold that density. And I basically sort it, and I pick the guys which have very low density first, and the ones that have very high density, they are the really typical ones. Huh? Sounds like a plan, right? If you look at some data statistics, so if you look at just the unnormalized density, and actually this should be more of a straight line, but anyway, here's what you get for typical data on handwritten digits. And here are some really ugly ones. And yeah, they are ugly. Are they the ugliest ones that I could get? I don't know. So if you think about what's going on with density estimation, it's actually really stupid. So, I mean, we don't really care whether we are doing really well in the high density regions. After all, we are after the outliers, so we don't really care about modeling the typical case terribly well. And the other thing is we don't really care about a specific density value. What we care about much more is just that we know it's below a threshold. And we might actually, ask for a specific fraction of instances. And we want to really tune our algorithm to, do well for, the bottom 1%. So the problem is that my density estimator will typically try to do really well for the very high density regions and do poorly for the low density regions. So if I use my density estimator, I'm going to use a device that's engineered to do poorly for the regions that I care about. Bad plan. So the key insight is that actually the area of low density I can approximate as the label set of some auxiliary function. So I don't really need to estimate P of x. I just need some proxy for this thing. So I just need some function f such that it's normal if f of x is below a threshold, and well, this f of x then describes, the degree of novelty of unusualness. Let me show you that on a picture. So, let's say here's my density. Has all the nice properties, integrates up to 1 and all that. And so we care about low density regions, so I'm going to maybe put the threshold here. So it's going to pick this set, this entire region here. It's going to pick this. It's going to pick this. And that's what I'm going to, declare to be an outlier if I see any data in it. Now if you think about it, it doesn't really matter what this function does above the threshold. Right? It could do anything. Right? And that would be still good enough, as long as it does a reasonable thing in the low density regions. Furthermore, whether I have this curve or I have this curve here, doesn't really matter either, so I could rescale it, and it's just the threshold that matters. Now, it turns out that actually getting those two things right are usually the really hard bits for density estimation. So one is computing the log partition function, and the other one is, getting the scale right. So, can we get rid of it? Let's just start with, our density estimation problem. This is what we would have in exponential families. That's what we saw, I think, 2 weeks ago, when we looked at exponential families. So, it's sort of nice, but getting your hands on this theta, g of theta, is really hard. Because that's basically the normalization. So, now the next few slides are essentially just what I showed you. So can we fix it? Yep, we can. And I'm going to transform this optimization problem here into novelty detection problem. So the first thing I'm going to do is I'm going to look not just at the log likelihood of the instances, but look at the log likelihood and compute it with regard to a reference score, e to the rho minus g of theta. Now by picking this reference score, this is constant after all, I'm getting rid of the entire scale. Furthermore, I'm going to look at this score only if it exceeds, some threshold rho. So we are taking our density estimate from exponential families, and we're throwing away, the normalization, and we're picking some threshold above which I don't really care about things. And of course, this is suitably chosen such that we get exactly this expression here. So for exponential family, this is what comes out of it. Now we don't have to normalize with g of theta anymore, and we don't really need to do particularly well in high density regions, and what we had before as a possibly rather unpleasant convex program now becomes a quadratic program. Okay. So here's the optimization problem that you get. And I wish we had come up with the entire optimization problem the way I just explained it to you. We came up with this by essentially sitting around with a few cups of coffee and joking what happens if you go from a 2-class support vector problem to a 1-class support vector problem. Then we started wondering, does it actually do something useful? And we realized, yes, it does. And that's how this algorithm actually really came to be. But afterwards we convinced ourselves that it's actually a meaningful thing. So here's your data, you're trying to find the hyperplane that separates it from the origin as well as possible whilst, while still, being closer to the origin than all the time. And, that basically means minimizing 1/2 norm of w squared under the constraint that w of xi is greater or equal than 1. Or then if I want to add slacks, I just add them as here. So I get the optimization problem again, right? And then, I compute the Lagrange function. Same thing exactly as what we had. Take the optimality conditions, and voila, here's our dual problem. So I basically minimized, alpha transpose k alpha, so this can be kernelized just as well, minus some of the alpha i's, under the constraints that the alpha i's are between 0 and c. So this is very easy to do. Now here's a third interpretation. So this is due to two guys called Tax and Dewey. They had this idea around the same time as when we came up with the novelty detection. So what they said, well, if we have data in some space, can we find the minimum enclosing ball for that data? I think a precursor of that is actually due to Chris Burgess. But in any case, so that's around 98 or so, maybe 2000. And you can write that also as a quadratic program. Find a minimum enclosing ball. And you can actually show that this is equivalent to novelty detection problem in the case where all the points lie on the surface of a sphere. Now, okay, can somebody tell me an example where all the points lie in the sphere in a support vector machine? Okay. How would you measure the length of a vector in Hilbert space using a kernel? Well, it's a very simple thing you can do. Well, the length of a vector, phi of x, I just square this term, right? That's the length squared. Now that is nothing else than the inner product between phi of x and phi of x. And I know what that is. That's my kernel, right? That's k of x and x. Now for radial basis functions, which depend on the distance between x and x prime. So if I have something like, e to the minus lambda norm of x minus x prime, if x and x prime are the same thing, that gives me a constant. In this case, for instance, 1. So what I've therefore got is a situation where in Hilbert space, all my points lie on the surface of a sphere. It's a very bizarre construction, right? They all have unit length. And in that case, this algorithm is identical to the, single class SVM problem. You can immediately see, if I want to find, the smallest ball, this is equivalent to be finding a set where I just push that hyperplane out as far as I possibly can. Because the intersection point is the same. Yeah, just if you look on that cap of the ball, you'll see that it defines the same set. And then if you look at the optimization problem, you'll also see things matching up. Now, there's a little problem. Remember this car alarm, right? I would like to set it in such a way that it annoys the neighbor on average once a week. So how can I do that? So if I build my single class SVM problem and I pick some value of C, well, the number of points that I get will actually be variable, and I would rather like to fix that. So here's what we can do. I basically pick a hyperplane that separates the data from the origin, and I make that threshold adaptive. So as I make it sufficiently variable, I can actually pick a threshold in such a way that I only pick the instances that actually make up maybe 10%. And so all I now need to do is figure out the mechanism to automatically adjust rho while I'm also finding W. So I'm going to show you the optimization problem that goes with it. And as it so happens, again, we had the optimization problem first, and then we figured out what it did. So here's our standard optimization problem. Now, rather than having w.x is greater or equal than rho minus psi I, 1 minus psi I, we have rho minus psi I, right? And now we impose an additional penalty on m times nu times rho. And these parameters are suitably chosen such that afterwards we'll get just the right problem back. So, first, have a look at the dual problem. I mean, this is really handled cranking, so I'm not going to go into detail. But basically, it's really the same, almost the same problem as what we had before. We have a purely quadratic objective, constraints between 0 and 1 for each coefficient, and the sum over the alpha i's being nu times a. Okay. So here's a cool theorem. It says that the solution of this problem satisfies that at most the fraction of nu points are actually novel, that most the fraction of 1 minus nu points are not novel, and that anything that sits exactly on the boundary vanishes for very large in the limit. Okay. So let's prove that graphically. So here's our hyperplane. Here's some points. They do whatever they do. Here's some points on the boundary. And here's some points that are on the wrong side of the boundary. Now, if I change rho, okay, so basically these are all the slacks that I'm paying. But the sum over those lines is what I'm currently paying for into the origin. Okay. Now if I move my margin by a small fraction, let's say, delta rho to the right. Well, what's going to happen is that all these points here will increase their slacks by delta rho. Furthermore, all those points here will now also have to pay. So it's basically points on the left-hand side plus the points exactly on the margin, on the boundary. So I pay an added penalty of delta rho times m plus, and I gain minus nu times m times delta rho. Basically this term. And of course, that gain has to be negative if I were to do this. Otherwise, I would actually get a different. Now, if I were to move this hyperplane to the left, then, if I move it a little bit, well, the points on the boundary don't really gain. The points that are really wrongly classified, they all gain. So I get delta rho times m minus nu times m times delta rho. Okay, these are the changes. I need to make sure that they're both negative. So if this is less equal, sorry, they actually need to be greater than 0 because I'm absolutely. And since I'm moving in the other direction, I basically need this is greater than 0, and this is less. Because the sign of those delta rhos is different. So plugging things in, I get the following condition. Mu times m times delta rho is less equal than delta rho times m plus, which is less equal than delta rho times m minus. Just combining these two conditions. Right. So I can go and divide out delta rho. This was infinitesimal and arbitrary. I get this condition here. M minus is less equal than nu times m, less equal than m plus. That's exactly the condition. That's this new property. Yeah, I think we spent more time thinking about which Greek name we should give the variable than the proof. To make it a really horrible pun. Yeah. Now, to prove that the fraction of points here on the boundary vanishes in the limit, you need to make sure that this is actually a set of measure 0 and will stay that. So basically you need to make sure that this boundary can flex and twist in such a way that it hones in exactly on some discrete component of the distribution. So you need to make sure that your distribution is well behaved and that your kernel is well behaved. So this is actually a special case of what later on Steinbart proved in terms of number of support vectors scaling with the amount of data. Just a proof. So let me show you a few examples. So there's some data, and you probably see some dots up here if you could see them. And it's basically playing with different values of nu and different kernel widths. And so what you can see is that as you, in this case, that's actually there are no outliers here. As I add the outliers, the typical region doesn't really change very much. Now, as soon as I go and actually make that threshold to be 0.1 rather than 0.5, well, it picks up some instances here. And if at the same time I go and actually keep the threshold at 0.5, but make my function class very flexible, it'll also go picking up things. So those two things are clearly interrelated: smoothness and how much I regularize, and that's exactly what you would expect. That's essentially what model selection does. Model selection comprises at least of two things. One way is how you actually order functions relative to each other, basically which function you consider a complicated or simple function. And the other thing is, of course, where you draw the boundary. So to put it into pictures, if this whiteboard is a space of all possible functions that I could use, then I could find some increasingly larger and larger set of functions which have different degrees of complexity. Maybe I give that the value 1, 2, 3, 4, 5. So if I then decide, okay, I'm going to pick a function class with complexity up to 2, then okay, these are all the functions that are okay. And so that's fine. Now I could equally well decide that I would pick a very different class of function. So I could have this as my complexity penalty. Under certain equivalence properties, eventually as I make those coefficients large enough, they will cover the same space, but they will do it in very different order. So this is basically where the engineering comes in. You as an engineer who solves a specific problem need to have a good idea of whether you should pick the red or the blue set. You as a statistician will then need to figure out exactly what threshold to pick. And provided a large enough amount of data, it doesn't really matter whether you did a good job at engineering. In reality, it makes a big difference. So I'll show you some even uglier digits than before, and I guess most of you would agree with me that these are really ugly digits. Okay. By the way, if I set new equals 1, you can check, you get the Parsons Windows estimator back, and you can check that very easily. It's still a problem, right? So let's set new equals 1. So then I have sum over the alpha i's equals m. And I know that the alpha i's are between 0 and 1. So the only way I can get that is if all the alpha i's equal 1. In which case, it doesn't really matter what my objective is. I just get to the solution all the alpha i's equals 1. At which point, well, I have Parsons Windows. Now you can do that also for classification, and you can use exactly the same trick as before, and then depending on whether you pick a simpler or a more complex function class, you will get more or less meaningful solutions back. The key point actually in this slide is that if you pick the right function class, then setting the value of new doesn't really matter so much. Overall, it's a very convenient thing, because in practice you will typically know what error to expect. So if somebody gives you a classification problem, they might actually tell you, well, before that we got an error of maybe 10%, or the human error rate is in that order. So it's a good idea to just start off with that value. That's a much more meaningful thing to do rather than picking some regularization parameter otherwise. And then there are ways how to adjust the function class, and we'll discuss that a little bit more next week. Basically how, for instance, for the RVF kernel, you can pick a sensible scale. And so with some very small modifications, you get an algorithm which doesn't actually require much tuning to get something decent going. Another question? Yep?
I'm not sure if I understand this one class classification problem. Don't you do the same thing with two-class SVM by relabeling positive example, so 1 through 9 as positive, and all the crop to be -1 negative example?
Okay, so if I have outliers and I have them labeled, I'm in good shape. Then everything's fine. Then I don't really need novelty detection. If nobody tells me what novel instances are, then I'm in trouble. And this is basically exactly for that case. However, what you asked is actually a little bit deeper than that. Namely, you can, as a matter of fact, take single class SVM and take labeled instances as the data, and you want to find the unusual instances in that case. Right. So I just take the digits with their label as an instance as a whole. And then I run novelty detection on that to find out which instances are unusually classified. And it turns out that, for instance, for binary, you get exactly binary classification back, which is actually rather surprising. Okay. So before we go into structured estimation, I would say we probably can take another short break, and then we're off to